So let's take a look at RSA. So in RSA, first you have to generate a key. So you have to choose two large primes, P and Q. Then multiply them together to form N. Then you calculate phi of N, which is P minus 1 times Q minus 1, and that's actually going to be the number of those N numbers you can actually use. Those are the values around that circle of modulus N that actually have inverses. Because if I was to choose P, for example, then as I multiply it by a number, I'll just hit multiples of P. So if I'll never be able to undo that, it's not going to hit all the values. That's a destructive transformation. If I multiply my message by P, I'm not going to be able to multiply by anything to get back to my message because I'm only going to hit multiples of P. It's the same as using AND or instead of XOR. I've engaged in a transformation that lowers the amount of information in the data. So that's why this is the actual number of values around the ring that you can use to encrypt and decrypt. And then you get a public exponent which is designed, so it has to be relatively prime to phi. Doesn't exactly have to be a prime number, but a prime number will work. And then the private key is designed so that D times E is 1 mod phi. Remember, phi is the actual number of values you're going to use around the ring. And so if you encrypt with E, you can decrypt with D because the product of them is 1. So those are the two things you need. You need the encryption key and the decryption key. So you choose two primes, which, by the way, can get pretty tough, and we'll have later projects where we talk about how to find large primes. In this case, we're just going to use small primes to see how it works. We're going to use 7 and 23. Then we calculate N. So let's start doing it. We run Python. I'm just going to do it in interactive mode. So I set P is 7, Q is 23, N is P times Q, and then print them out. So here's P, Q, and N. So N is 161. All right. Now I compute phi, which is just P minus 1 times Q minus 1. So that's 132. That's phi. Now I can pick a public exponent, and you typically just use the same number, either 5 or 3 or 65, 537. People typically choose common numbers. It's not a secret, E. So now then you have to find the inverse, which is not simple. So here we're going to have E is 5, and we're going to start calculating some multiples of E. Now, if you think about it, phi is 130. So 5 times 20 is 100. So there's no possibility. Now, I'm going around a ring. In fact, I think I have a picture of it here. I'm going around this ring, right? So I'm hoping to find 1. So if I start with an E of 5, and I start making it bigger, I can't possibly hit 1 until I've gone around at least once. So there's no point in bothering anything lower than 20. 20 will get me around to 100. So I'm not going to bother looking for anything smaller than 20. I'm trying to find a number which, when multiplied by 5, equals 1 on this ring. So I'm going to start with N equals 5. And now 20 times E is 100. All right. So now what I need to have is I want to print various values times phi of N. So if I try this, you can see, just to see how the ring works, here's some numbers. 100 mod phi is 100. 130 is 130. 131 is 131. But 132 is 0. Because phi is 132. That's my modulus. So that's how modular arithmetic works. I go around the ring, and then I hit 1 again. And at some point, I'll make enough trips that I'll hit a 1. So now I'm going to take 20 times E and 21 and 22 and 27. I'm going to try all these numbers. This will get me enough multiples to pass the place where it wraps around. So there we are. See, I made it 100, 105, 110, 115, 130. It goes past and turns into 3. So I didn't ever hit 1. So I did not find an inverse in this range. So again, there's no point trying numbers until I get up to about 2. I think the second cycle, and that's in the range of 50. So here, if I try them, there we go. I get 50. Here we are. 50 is 118, 51 is this, 52 is that, and 53 is that. That's the inverse. 53 times 5 is 1 in modular arithmetic. So the encryption key is 5, and the decryption key is 53. And I could only find that if I knew P and Q, because I had to calculate 5 from P and Q. So this is a secret, the decryption key. This is a number where only the holder of the private key has it. So that's the game. Now this is how it works. So Megan here has created, the public key is N and E, 161 and 5. She puts it on a public server where anybody can find it, and now you can receive secrets. One of the fundamental problems with public key encryption is it only works in one direction. It's like putting a slot in your door to receive mail. Now anybody can send you mail, but you cannot send anything out. You can receive secrets. So you publish this. Now anybody that wants to send me a message can encrypt it with that, and only Megan can decrypt it, the holder of the private key. Unless, of course, you can deduce the private key from the public key, and you can when it's this short. But when it's longer, that becomes impossible. So that's what goes on. She has all these secrets, P and Q, and she has N and phi of N, and E and D. She knows all these things. The other people sending messages only know N and E. So Q-Ball wants to send a message. Now I somehow have to encode letters into numbers, and what I'm going to do is just encode them with ASCII. So he's going to send HI exclamation point. So the message is going to be these three numbers, 72, 105, and 33. Those are the numerical values of high. So the way you encrypt is you take x to the, back. All right, you take x to the E mod n. X is the message. You take it to the power E mod n. That's how you encrypt. So he's just going to do each number separately. So here's the encryption process, 72 to the E mod n, 105 to the E mod n, 33 to the E mod n. So the message, encrypted message is 151, 119, 157. All right, to decrypt it, this is now what you call Y. X is the plain text message, Y is the ciphertext. And to turn the ciphertext into the message, you take Y to the D mod n, because Y is X to the E, and this is X to the E times D, and E times D is 1. So this gets you back to X. That's the point. And D, you can only get if you know the private key. E, everybody has. So everybody can send you messages, and you're the only one that can decrypt it, the holder of the private key. So all she has to do is take these numbers, 151, 119, and 157, and take them up to the D mod n. And that turns them back into the original message, 72, 105, 33, which you can then look up in this chart. And 75 is 72, right? 72 is an H. Yeah, 72 is a capital H, and a lowercase I is 105. Yeah, and an exclamation point is that other number, 33. Yeah, so that's the simplest. That's what happened. And so now there's a couple of challenges here where you have P and Q and E, and now you got to calculate the public and private keys. And then you're going to get a message sent to this person that you have to decrypt, and so on. So you get to practice with these short keys. All right. And we stop this one.